All right. This is a little bit of a short video to explain homework 2. Okay. Actually, this may just take 10 minutes, I think, or less. It's a short one. Okay. All right. Homework 2 will be posted today, and it contains 4 problems. Okay. Again, don't get scared with the explanation. More explanation, the longer the problem explanation, the easier it is. Okay. Right? If I say prove E equals mc square and stop there, that's going to be a difficult problem. So just one line problem statement. Okay. But if I give you a lot of hints, and it's easier. Okay. So don't get overwhelmed by the project explanation. Okay. Or the assignment homework. Okay. Homework 2 has 4 problems. First problem, actually, I think you can solve the first 2 problems without actually watching the second set of videos. Yes, yeah. So problems 3 and 4, you need the videos for the week 2. Okay, but problem 1 and 2 you can get started. So if you do need the to get started, if some of you have finished the first homework already, then you can get a jump start here. Okay. Anyway, the first problem is actually it is related to homework 1. Okay, and I've given you the grammar from homework 1. Okay, so this is the grammar from homework 1. Okay, so consider the following grammar for data log atoms for homework 1. Okay, you must use exactly same grammar for this one. Okay, given here, and you need to do produce a leftmost derivation. Okay. If you don't know what a leftmost derivation, I think it was covered in the first set of videos. Yeah, that's right. I think the derivations and parse trees were covered. Okay, so for this particular input, you need to provide a leftmost derivation. Okay, so you can look up the format in which it goes. So you need to write atom first, and then you put the equal signs and greater sign, and then say what it derives in one step, which will be this one right hand side, and then you take the leftmost non-terminal. In this case, it's args, and then you choose one of these 2 rules to expand that, and so on until you get to this point. Okay. And by the way, when you get to number, when you replace arg by number, you don't have to say you don't have to put number token. You can actually put its value there. Okay. Otherwise, the whole derivation takes extra steps. Okay. So when you go from arg to number, you can directly go from arg to 20. Okay. Same thing from when you go from arg to when you replace arg by string, you can replace arg by John. Okay. And same for the arg by name, you can replace arg by x or y. Okay, so that's how I have shown the derivations in the slides. Okay, so you have to produce the leftmost derivation. Okay, this should take a few minutes. Okay, and also the parse tree. Okay, so you need to construct the parse tree. Okay. And also again 2 minutes. Okay, so this problem is a gimme. I do want you to draw this by hand, I guess, or if you want to use one of the drawing programs, you can draw for this part. You don't need a drawing program for the derivation, so you can just type it out. Okay. With the equal greater sign after each step. Okay, but this parse tree, you can use one of the drawing programs and produce a JPEG and then include it in your submission. Okay, because I do want you to submit one these files for this homework. Okay, homework 2, and one of the files is homework2.pdf. Okay, and I explain later on what goes into this and what goes into that. Okay, so this solution will go into homework2.pdf. Okay. So whichever way you want to do it, but first solve it, okay, and then you can present it. So that's the first one, easy. Okay, this should not take much time at all. Okay, it's just a derivation and the parse tree. Okay. All right. The second problem is to write a grammar. Okay, so like I said, it's an art skill which you will hopefully learn. Okay, and you've already seen. I've given you 2-3 examples already. Okay, but this one again I have laid it out. Everything is laid out here. Okay. And also some examples are here. Okay, but this also is a nested structure, and not also almost every grammar you look at will be nested in some manner or not. Okay. Okay, I hope most of you are familiar with JSON. Okay, JSON is a very popular data format. Okay, used in web and also on other system software, for example. Okay, when you write compilers and a lot of other type of software. Okay, there's a lot of configuration information stored in JSON format. Okay. So for example, node.js, okay, if you see that there's a lot of JSON in that system, okay, in the node infrastructure, okay. But also JSON is used for APIs, okay. If you've done any bit of web programming, you better be good at JSON. But anyway, hopefully you've seen it before. If not, learn it now. Okay, this is another one of those things which is a must know for a computer scientist. Okay, what JSON is and how what's it used for. Okay, but anyway, we are not going to use this JSON. We're just going to build a grammar for this. Okay, so a JSON, I think this is actually probably 90% of what is allowed in the full-fledged JSON. Okay, but maybe I may have I probably have simplified some of the aspects of JSON. Okay, but this is okay. There are two non-recursion stopping cases here. Okay, and that's a string and a number. So a number. So this looks very much like some of the WAE and so on. Okay, examples. So number like 25 or 25.0, that kind of things. That's a JSON expression by itself. Okay, and also a string constant in double quotes. So this is very similar to the homework 1 kind of thing. Okay, so those are the two basic type of JSON expressions. Okay, a string constant or a number constant. Then we have a JSON object. Okay. And the fourth is a JSON array. Okay, what's a JSON object? A JSON object begins with the left brace. If you want, you can see an example here. Okay, or if you want, let's see a nested one here. Let's look at this part here. Okay, so it begins with the left brace. Okay, so it says it starts with the left brace, and it's followed by a list of key value pairs separated by commas. Okay, so there's something, comma, something, comma, something, comma, something. Okay, and then ends with the right brace. That's all. Okay, so it's basically list structure. So you can actually see that the same pattern can be used in the grammar. By the way, the grammar for this is again, if you take more than 5 minutes, that means you're not paying attention. Okay, this is again the same list pattern, and I spelled it out here. Okay, got it. Okay, so that's so there are 3 parts to a 3 parts to an object: a left brace and a bunch of things and a right brace. Okay, those are the 3 parts, and the bunch of things is separated by commas. Okay, and what is a thing there? A thing is a key value pair. Okay, and what is a key? The key must be a string constant like that. Okay, very much like a string constant like that. Okay, so the key must be a string. Okay, but the value can be any JSON item. Okay, expression. So the value can be JSON. So that's what gives the power. Okay, so you can actually nest now. Okay, so you can actually put in the value. You can put a basic JSON expression like a number or a string, or you can put an array if you want. Okay, you could put an array there, and there's an example here. Okay, next to the phone there's an array here. Or you can put another object. So that's how you nest an object inside an object. Okay, so this object is nested inside this object. Okay, got it? So any one of the 4 values can go there. Okay, so that's what a value is, JSON value. Okay, and the array is also simple. Okay, it instead of a brace, it starts with a bracket. Okay, and then followed by a bunch of things, followed by a right bracket. Okay, so that again is very similar to that, except that the bunch of things here is even simpler than before. The bunch of things here is a bunch of JSON objects itself. Okay. Not objects, JSON expressions itself. So you can actually have numbers or strings or arrays. So you can actually have an array inside an array, or you can actually have an object inside an array, or you can actually have an array inside an object, and so on. All these things can get mixed and matched nicely. Okay. Anyway, so here are some examples. Now, by the way, each line here, this one is one example. That's another example. That's another. Okay, but this is one example. This whole thing is one example. Okay. Maybe I should leave a blank space. Yeah, I might do that. A blank line between each of these. I'll try to put a blank line. Okay, so that let me see quickly within half a second here, because the last part is a multi-line JSON expression. Okay, summer flash homework 2. Okay. So it's here in my here, right? So we just go and put an this is pre-formatted, so I should put a line, blank line. Oh, not here, okay? Because this part is all together, okay? Yeah. So I think that should do it. Let's see. Yeah. Let's look here. Yeah, that's right. So now you can see that the 25 is coming by itself. The Jones is by itself. Okay. This all, but this whole thing is one expression, JSON expression. Okay, so for this you'll write the grammar. Okay, so that's the first part, write a context-free grammar. Okay, then what I want you to do is I want you to take that grammar and also the tokens which you're deciding. Okay, and put them into the PLY system, okay? But not all the way. We'll just write the lexer and the parser, and you can see that write the context, then input the grammar rules into PLY, lexer, parser, and main, and test. I have given you the main, by the way, okay? So you don't have to write the main. So this is the main program, and you'll see that when you call the parser.parse, we expect a Boolean value. So your job would be, rather than construct a data structure in the parser, you'll return a Boolean value of true or false, okay? And true, and actually only in one of the functions you have to write that, okay? And that's the first function, okay? So you'll just return true for p sub 0, okay? In the first function. In all other functions, you will not, actually you'll not even have the p sub 0 assignment statement. So this should be very trivial work, okay? So anyway, I want you to put it, use my main program, and then write the lexer specification quickly, and then the parser, take the grammar rules and put it into the parser, and define the functions, and don't even do the assignment statement, p sub 0 assignment statement. You don't have to do, except for the first one, in which you'll say p sub 0 equals true. That's all, okay? Got it? And then you can run this program, okay? And then you can actually provide JSON expressions, and the program will return valid, valid, or invalid, okay? Got it? If the syntax is valid, it'll say valid. If the syntax is not valid, it'll say invalid. So this is a good way to test whether your grammar and everything else works well, okay? All right, so that's problem 2. Problem 3 and 4 are topics which we haven't covered in the lectures, but you will, hopefully you'll start watching the videos, lectures for lecture 2. And I may talk a little bit about problem 3, because I think I can explain to you without actually talking about what the attribute grammar is. The problem at least I can explain, okay? And then the 4th is denotational semantics, okay? So those are the 2 problems which you will have to watch the videos to understand what these 2 are, okay? But let me talk about this assignment number 3, problem number 3, okay? So for this, we will take the grammar from the slides, which is the WAE grammar, okay? These are the 11 rules we saw in the slides, okay? Exactly same, okay? This includes the with expression here, okay? And this assignment number 3, problem 3, deals mostly with the with expression, okay? Even though you may have to work on all of that, but the focus should be on the with, okay? And what we want to do is we want to build attribute grammars. Again, what you have to watch the videos to do that, okay? Which will do in part A. There are 2 parts here. In part A, what it'll do is it'll check to see if in the with part, in the variable value part, okay, in this part, okay, whether there are any duplicate variables, okay? So see, if you say x is 2, y is 4, and x is 5, okay, that doesn't look right? Because then which x, what is the value of x? Is it 2 or is it 5, okay? Correct? So that is not a good thing to do when you write this with expression, correct? But unfortunately, with the grammar which we have, those 11 rules here, that grammar has no capability to check whether this variable is the same as that variable or not, okay? Got it? So it has no capability, okay? So you would accept this and say this is a valid string. So, but then in your main program, you may have to check whether this is the same or that, okay? But there is this new concept we are going to learn in the videos called attribute grammars, which has a very interesting way to check for this in the grammar itself, okay? And that's what an attribute grammar is, okay? And actually, the PLY system implements an attribute grammar, so actually you should be able to code that check inside the PLY, okay? And that's why this is sort of related to the PLY. But anyway, in the first part, you will check for this extra check you'll make, besides the grammar check, okay? You'll actually check whether any variable is repeating here or not, okay? That's one. And then the second part is, suppose you had a with expression here, okay? Let's say this part here, okay? Which is embedded inside that, okay? Now you can see that you have x is 2 and y is 4. That problem is not persisting here, okay? But then we have this inner expression which is plus xz, okay? Now that seems problematic, because we have given value for x, which is 2, but we have not given a value for z, which is 4. Unfortunately, we have given it for y, which is 4, but z, we have not given it a value, excuse me, right? So it'll be impossible to evaluate that, correct? So this check, again, whether this whole expression is evaluable or not, okay, whether can we evaluate this or not, again, is beyond the capability of this grammar, okay? So there are 2 problems which this grammar cannot catch, okay? And so we want to catch these 2 problems with attribute grammars, okay? And that's what I want you to do. I want to build attribute grammars for this and for this. I don't want you to build them together in one grammar, okay? It's possible, but I want you to do them separately, independently, okay? So when you're doing part A, you don't have to worry about the problem in part B, okay? And vice versa. So these are independent. That's what I talk about here, independently, okay? So I want you to build, write the solution by hand first, the attribute grammar solution, okay? Again, you have to watch the videos to learn how to write this, okay? And then after you do those two, part A and part B, by hand, you'll actually implement it in PLY, okay? And here I have shown you the main programs, okay? I have given you the main programs, and also the lexer is the same as what is available here, okay? You can use the same lexer because that part has not changed. So the lexer and the main program is given to you. And also the parser is given to you here, okay? This parser you can use exactly as it is, but you have to sort of modify that slightly, okay? Very slightly. And actually the code modification is very, very tiny on that. But you have to think about it and how the attribute grammar can be. So basically that P sub 0 assignment statement is what you'll modify in this, okay? So the point is we are not going to make a data structure construction here, okay? We are just focusing on this check here, that's all, okay? We are not worried about the data structure, okay? Got it? So again, this will return a true or false eventually, but internally it may be doing some other things, okay? It may be maintaining some data structure, but eventually this will return a true or false, the first function, okay? And then the main program, you'll see I check if it's true or false, and then if it's true, then I print that false like that, okay? All right, so the part third is also sort of related to PLY, but you have to learn attribute grammars before you can actually attempt to do this, okay? And the final problem, it's denotational semantics. Actually, if you look at the last 4 slides, 4 or 5 slides, I think so, 4 slides, I think so, of the second set of slides which I'm going to post, okay, you'll see a particular denotational semantics is being developed, and this is just taking that solution and extending it to a couple more constructs, okay? Okay. That's all the explanation I wanted to give on homework 2, and if need be, once you watch the videos, I can maybe post another short video on explaining what an attribute grammar, or you can check with me in the office hours. Okay, take care.